Hey everyone, we're going on to chapter 8 here. We're going to look at this idea of linear momentum and what that entails. If we see here, we've got a guy that is hitting a golf ball, so obviously this idea of momentum is going to have to deal with objects in motion, just like everything we've done so far. So let's see what that's going to entail. The first thing I want to investigate here is a crash. We're going to show you a crash here, and I want you to observe the motion and talk about some of the things that we can measure in this crash. So looking at the motion there, you can see that the cart is initially at rest. I give the cart a decent push. It flies off that spring and returns back in the opposite direction. Looking at the motion there, it looks like that motion is pretty steady. The only thing that looks different is that it is changing direction. So it's going from heading to the left to now heading towards the right. And the motion before and after really looks the same steady speed, just completely opposite directions. The cause of it changing direction is going to be that spring over there. That spring is going to cause a force, and that force will cause the cart to go in an opposite direction. It'll accelerate it from heading to the left to now heading to the right. We're not necessarily looking at any constant velocity scenario here because the velocity is obviously changing. And if we wanted to assume that it was a constant acceleration in our scenario, we would have to assume that the force was constant. However, we're dealing with the spring force here, and the spring force we know is not constant during any of our trials. Force in a spring changes based on negative kx. So that spring is getting compressed and trying to push back on the cart in the opposite direction. So a couple things that we can measure here. We can measure the velocity before and after. I do have it set up so that we can have a motion sensor on that track, and we can figure out how fast it's going before it hits the spring and how fast it's going after it hits the spring. A couple other things we can measure is the force that spring's actually feeling. That spring's actually plugged into one of our force sensors, so I can measure the force it feels during that collision. Recap of our issue. The cart moved forward, hit a spring, and moved backward. It looked like it was going around the same speed. I mean, go back and watch the video again. It looks like it's going the same speed before and after. However, the velocities are different because the direction is changing. Spring forces are what's causing this change. It's causing an unbalance in force and making us accelerate, but it's not a constant acceleration. A couple of things we can analyze here are the force time graphs and the velocity time graphs. Let's take a look at both of those and see what's happening. In the velocity time graph here, you can see my velocity going from a positive velocity in the beginning and sharply changing to a negative velocity on the way back. The cart was heading towards the sensor, then the cart was heading away from the sensor, and that change in velocity happened very quickly. So there was a very big acceleration experienced, but the acceleration, like we said, was not constant because we're dealing with a spring force that does not push the same every single distance. So the velocity graph was pretty straightforward. Velocity was heading to the right, hit the spring, and velocity was heading back to the left. So there was a big change in velocity caused by the spring force. Let's analyze the force then. Let's see how that... So here's the force time graph. You can see there's no force. Ooh, and a gigantic spike right there. Let's watch that again. No force, spike. That spike is when the cart hits the spring. When the cart hits the spring, it imparts a really large force. It grows until it looks like a 32 Newton max, and then that spring force dies off as the spring separates from the cart. So during that collision, the collision did not take a lot of time here. If you analyze that very, very carefully, it looks like it's tenths of a second, or from the forward direction to the backwards direction. So there was a very large force for just a very, very brief amount of time. So you experienced a very large acceleration over that brief amount of time. So what does that mean? What does that mean for the change in motion of our cart? What it means here is that we have a small force in the beginning and a very large force in that peak. And we've analyzed force graphs before, but we've looked at force position graphs. Now this is a force time graph, force as time goes on. And if you look, we can kind of analyze the area of that because that force isn't constant, but if we take an average of those forces, you can see that area in yellow there is the area under the curve. And if I break up that top area where the peak force is, all this shaded area that's missing equals that top area there for the force time graph. So with the force time graph here, we can take the area under the curve to analyze how the motion changed. So over that time interval, that force from the spring caused the mass to accelerate. And what is the meaning of acceleration? Well, acceleration is the change in velocity over time. And we're having a very quick change in velocity over a very small change in time. So if I want to just analyze what was going on with the change in motion, if I want to look at how the mass and its velocity was changing, I just really want to focus on this m times dv. So to do that, I have to move dt to the other side, and I get force multiplied by the change in time equals a mass times a change in velocity. And this is how we can analyze changes in motion. A change in motion on the right side of this equation, m dv dt, equals a force times the change in time. So because the spring pushed on it over a certain amount of time, that mass changed from heading to the right to heading to the left. So we have a name for this. The name for this area under the curve, this force dotted with time, or mass multiplied by a change in velocity, we call that an impulse. An impulse, for whatever reason, is labeled J on your equation sheet. So it's a change in an object's momentum, a change in an object's motion. So if you look at that, J equals m times the change in velocity equals the average force multiplied by time. If the force graph looks like a triangle like we had before, just find that area under the curve and you'll be good to go. If you look at our units, mass is measured in kilograms, velocity is measured in meters per second, and force is measured in newtons, and seconds is measured for time. So what it's saying is that our units for a change in momentum, or an impulse here, is kilogram meter per second or newton seconds. Let's make sure those units actually match up. So obviously I've got kilogram meter per second for my mass and velocity, but over here I've got newtons multiplied by seconds, and the equal sign means that these units need to be equal. But remember what a newton is. A newton truly is a mass multiplied by an acceleration. And when you multiply those two, you're going to knock out one of the seconds, and you do get the same unit here. So a change in momentum, or a change in an object's motion, is equal to its mass times its velocity. And there is no fun name for this. It is literally a mouthful, kilograms meters per second. So let's analyze this collision. Or when the cart came in and hit the spring, at 2.15 seconds, it was moving at a positive 0.45 meters per second. Not long after that, after the collision, 2.35 seconds later, the cart was heading backwards with a negative 0.44 meters per second in velocity. The cart has a mass of 1,010 grams, or 1.01 kilograms. So if we look at analyzing this, we'll figure out exactly how much the motion changed during that 0.2 seconds it was in contact with the spring. Let's analyze the force graph. Here's the force graph for that moment. You can see there's no force during the first few seconds, and when we reach that moment of hitting the spring, the force spikes, the force grows as the spring is collapsed, and then the force starts to shrink as the force gets weaker on the spring as it pushes the cart away. It maxes out around, looks like 9 newtons, so we're looking for the area under that curve. The area under the curve I can highlight with our data collectors here and calculate our area to be 0.9 newton seconds. So I know the area under the curve is 0.9 newton seconds. Let's head over to the whiteboard and see if we get our change in motion to match up with that. So our definition here for our impulse is force times time will equal our mass times our change in velocity. And in this section, force has a direction and velocities have direction, as you just saw me analyze the velocity time graph. So that means that this change in momentum and this impulse is a vector quantity, and you do have to worry about which way this change in motion is. So we said that the force times time, we already calculated that, came out to 0.9 Newton seconds for the area under the curve. So that should equal the other side here of our mass times our change in velocity. Our mass was 1.01 kilograms, and our velocity is changing from our final velocity to our initial velocity. We're going to subtract the difference between our final and initial speeds. So our final speed, we said the cart was heading away from the spring at negative 0.44 meters per second, and it was heading towards the spring at positive 0.45 meters per second. So since they are vector quantities, please be careful and watch the signs. 0.45 in for our initial velocity. We're going to put negative 0.44 in for our final velocity, and if you multiply that by your mass, you end up with 0.8989. So we have a negative change in our motion here, kilograms meters per second, which, if you look at the magnitude, is very close, and you can round that to 0.9 Newton seconds. But what's with the minus sign here? Well, the minus sign is because the block was moving towards the right in the beginning and heading to the left at the end. What caused that change in motion? Well, what caused the change for the cart to go from forward to backwards was the spring. And which way did the spring push? The spring pushed backwards. So technically, there was a negative force acting on it during that time period. So negative 0.9 Newton seconds is the impulse or the change in momentum. And 0.89 is what we measured with just getting our mass and our change in velocity. So as long as you have one side of this equation, you might be asked to solve for forces, times, or if they give you the area under that curve, maybe you'll be asked for the velocity after a collision happens. We'll analyze this more in class with demonstrations and example problems.